So, chapter 5, we're going to begin talking about some of the more, what do I want to say? This is probably the most difficult chapter in semester 1, just to let you know. So, I do need, your A game coming out of you. I will go slow. I will try to be very clear about what it is we're doing and how we're doing things and why we're doing things. If you don't understand something, I need you to make sure you ask, and I can explain more. But I just wanted to kind of prep you a little bit that this is one of the more difficult sections because it requires a little bit of creativity at points. Okay. So we're going to start by defining a term. So we say that an identity is an equality statement that is valid for all values of the given variable. What I want to do and what's going to happen are two things that have little to do with one another. It is not an identity. So, an example, what do we mean by an identity? So, maybe we have something like this. This is an example of an identity. It's a rather dumb one, but it's still an identity. Right? That's always true. Okay with that idea? Sure. 5. Now, for trig, we're going to have a number of important identities that we're going to use frequently, kind of starting in this chapter and then really not ending. So these are things that are going to be, some of these things are going to be necessary that, you remember from outside of this class and would be expected that if you took, a calculus course that you would remember some of these things next year, just to give you a heads up. Okay? So the first class of identities that we'll talk about are the reciprocal identities. And we've talked about these already. So each of our trig functions has a reciprocal identity. Remember when we defined cosecant, secant, and cotangent, we defined them as the reciprocals of sine, cosine, and tangent. right? So we have that same reciprocal relationship going on here. Notice that these two equations are just reciprocals of one another, right? And the same thing with the next pair, and the same thing with the last pair, right? These are some things that you'd be expected to kind of remember in perpetuity beyond this class. We'll talk about what kind of information we'll give you as we get closer to the test. But I would tell you right now, if you were in my calculus course, I would expect that you would remember these 6 relationships here. The next set of identities are the quotient identities. And again, these we've also kind of talked about already. Right? When we talked about how to use the unit circle to evaluate tangent, we talked about how tangent was going to be y over x or sine over cosine. Right? And if cotangent is the reciprocal, obviously cotangent is just going to be cosine over sine. Everybody okay with these? These are all things that we've kind of talked about already. We're just now formalizing and giving them a title to categorize them together. So the next set of identities we're going to kind of derive. Okay? They're all going to be based on this first identity, which is called the Pythagorean identity, because it's based on, surprise, surprise, the Pythagorean theorem. So, if we think back to our right triangle situation, what we can say is that sine squared theta plus cosine squared theta is going to equal, well, what's the definition for sine? Opposite over hypotenuse. So sine squared theta is opposite over hypotenuse squared. What's our definition for cosine in a right triangle? So that's going to be adjacent over hypotenuse. And because we're talking about cosine squared theta, that's going to be also squared. So how do we square a fraction? You just square the top and square the bottom. Hi, Lexi. Gabe. He told you guys already that he was leaving.
I forgot.
Okay. Notice now, excuse me guys, notice that these fractions have a common denominator, right? So we could add these together. So we can say that. And what is opposite squared plus adjacent squared equal to? If I go back to my right triangle, a squared plus b squared has to equal c squared. So the numerator becomes hypotenuse squared, which just equals 1. So that leaves us with the Pythagorean identity, sine squared plus cosine squared is equal to 1. No. A squared plus b squared equals c squared. Can we focus, please? The amount of side conversation is becoming a big distraction. The fact that I went through and showed you guys exactly what I did, and then 3 seconds later, you're asking how I did this because you were talking to your neighbor and not watching what I was doing, is a little bit frustrating. Not only for me, but for the other students that were paying attention. Okay, so if we can cool the side conversation, I'd appreciate it. I understand it's Friday and we're all very distracted, but we need to do a little bit better. Okay? So, why is opposite squared plus adjacent squared equal to hypotenuse squared? Because it's literally the Pythagorean theorem, right? Here's our right triangle. Okay? So, yes? Not with what you've just said there, but there is a way you could do the same derivation inside of the unit circle and make it work. Okay, next up is I'm going to use this. I'm going to use my Pythagorean identity here as a starting point, and I'm going to derive 2 other versions of this equation. Okay? So the first version that I'm going to derive is I'm going to just take this equation and multiply both sides by 1 over sine squared theta. Well, let's see what happens when we do that. So that gives me this, right? Everybody's okay with what I did there? I just distributed the 1 over sine squared. So what is sine squared theta divided by sine squared theta going to give me? 1. What is cosine squared over sine squared theta the same as? Cotangent squared and 1 over sine squared is cosecant squared. That's our second version of our Pythagorean identity. How do you suppose we're going to get our third version? Yeah, instead of using 1 over sine squared at the beginning, we'll use 1 over cosine squared. This is a new identity. I boxed the old one because we were done. So now we're going to do the same idea, but this time we're going to use 1 over cosine squared to multiply both sides. Everybody okay with how I got to here? What is sine squared theta over cosine squared theta then? Tangent squared theta, good. And then cosine squared theta over cosine squared theta?
1.
That's 1. And 1 over cosine squared theta is? Secant squared theta. That's my third version. So in summary, yeah, my Pythagorean identities are sine squared plus cosine squared equals 1. 1 plus cotangent squared theta is equal to cosecant squared theta. And 1 plus tangent squared theta is equal to secant squared theta. It's worth noting that when using these Pythagorean identities, it may become useful to rearrange these identities in such a way to make them more effective by like adding or subtracting things from either side. So for example, it might be effective to be using sine squared is equal to 1 minus cosine squared, or things like that where I've just subtracted the cosine squared from both sides. That is okay to do to modify these Pythagorean identities in such a way that it's useful to you. These are the only fundamental identities that involve any addition or subtraction, so I think these are the only ones that we can do that with. Fundamental identities. Okay. All right. The next topic, or the next set of identities, are called the cofunction identities. When we say co, what do you think co stands for? It stands for complementary. What? So, maybe some of you guys have noticed on your unit circle. Let me pull that up real quick. This will be a nice justification here. So let's look inside the first quadrant, and let's compare like sine of 30 with cosine of its complement. The complement of 30 is 60. So sine of 30 is 1/2. cosine of 60 is 1/2 also. So what we're seeing is that this co, again, is standing for complementary. Like cosine is really the complement of sine, right? So if we take that idea, we can package these together into some identities. Now, typically when we write these identities, we use radians rather than degrees, but you can just as easily think about pi over 2 as 90 degrees in your head. Right? So the first identity says, like, cosine is equal to sine of the complement. And the same relationship exists for tangent and cotangent. And for secant and cosecant. It is Kirch. And the last set of identities for this section is going to be the odd-even identities. So remember way back into section 1, we said that f of x is an even function if f of negative x is equal to f of x. We said f of x was an odd function if f of negative x is equal to negative f of x. Well, it turns out that sine, cosecant, tangent, and cotangent are odd functions, and cosine and secant are even functions. So we can say the following. I don't know why I switched to x's here. These could still be thetas. It doesn't really matter. Yes, Joanna. Sure. All right. So we've gotten through all of the identities now. I know that was a lot of them. what I would tell you is that the reciprocal, quotient, and the first Pythagorean identity would be things you'd be expected to remember in a future course. The other ones are probably things that, like, I should be able to remind you of this fact, and you should be like, oh yeah, okay. And okay. But those first, what was it, like 9 of them that I just listed are things that you will use enough that I'm sure that you'll end up memorizing them accidentally, but would be things that we'd expect that you kind of remember moving forward. So let's look at some examples now of things that we can do. So let's say we're asked to find sine theta if tangent of theta is equal to 3 and cosine is negative. So we've done this before, or problems similar to this before, using inverses. In fact, we just kind of got done doing some problems similar to this, right? We can also do this using identities. Okay? So, I'm going to start by choosing one of my Pythagorean identities. Which one of the Pythagorean identities would I want to choose? The one that involves tangent, because this is the thing that we know about. So I will start with 1 plus tangent squared theta equals secant squared theta. I know that tangent of theta is equal to 3. So I can replace the tangent with 3. 3 squared is 9, and 9 plus 1 is 10. Right? So far, so good? I can square root both sides to get the secant by itself. That'll give me plus or minus the square root of 10. And because cosine needs to be negative, what can I say about secant? It also needs to be negative because secant is 1 over cosine. So, because I know that secant is negative square root of 10, I know that cosine of theta then has to be negative 1 over the square root of 10. Okay with that? And because I know that tangent of theta is equal to sine over cosine, I know what the value of tangent is, and I know the value of cosine, so I would be able to solve this equation then for sine. So I know that tangent is equal to 3. That was given to me in the problem. Cosine is negative 1 over the square root of 10. That's what we just found. So to solve for sine, I would just multiply both sides of this equation by negative 1 over the square root of 10. Would I leave my final answer in this form? No. Why not? We have a square root in the denominator. How would I fix that? I would rationalize the denominator by multiplying the top and bottom by square root 10. What's the advantage of approaching the problem this way rather than using inverses? Look at the kind of answer I got. I'm getting an exact answer by doing it this way. Would you be able to get this exact answer if you used your calculator? No. So that is the advantage of approaching that kind of a problem using an identity as opposed to your calculator. Okay? My next example So the next example says to simplify the expression sine cubed of x plus sine x times cosine squared of x. When we say simplify, what do we really mean? Yeah, we're basically wanting to try to combine like terms to end up with an expression with less stuff going on than before. So we'd want a single term if we can get it. Right now we have two terms being added together. If we can turn this into a single term, that's good. If that single term is a fraction, we want to reduce as much of it as we can. Okay? So if I look at this, is there anything that you can see to do right away? Well, you can make sine squared into 1 minus cosine squared, but not sine cubed. Okay, you could do that. There's something much better to do than that, though. Let's start by factoring out the sine. Did you guys notice that in each of the terms, we have a factor of sine in there, right? So when I factor that sine out, what does sine cubed turn into? Sine squared. And what does sine x cosine squared x turn into? Cosine squared, right? And do you notice anything now? Yeah, sine squared plus cosine squared is 1. Nice. That is one of our 3 Pythagorean identities. It was the very first one. It is one of the 3 that I would expect that you would remember in a future course without having to be reminded. That's one of the big ones. Raul? Of course. And I know then that sine times 1 is just sine. So we'd say that this is just sine as our final answer. All right, let's look at this example. So, what do you think we should do here first? I would FOIL the numerator. One thing that I recognize right away in that numerator is what kind of foiling pattern do we see here? It's a difference of two squares, is it not? Do you guys recognize? Can you see that now? Looks like a little like x plus 1 times x minus 1, right? Which is typically good things happen when you multiply those things out. So if I do that, let's just FOIL it naively, like we don't really know what we're going to get. Okay. So we FOIL this out. Do you notice anything good happening in the numerator? No.
Sorry.
So if I look at secant squared minus 1, I don't have an identity specifically for that, but if I go back and I look at this third Pythagorean identity, if I subtract the 1 from the other side, I have this, which is what I have down there. So I can replace the secant squared theta minus 1 with tan squared. Nope, we can simplify this still a little bit more. So remember the quotient identities. I can rewrite tangent in terms of sine and cosine. Everybody okay there? And I'm going to think about that denominator as really sine squared over 1, because what I'm about to do is to divide fractions. So how do we divide fractions? Multiply by the reciprocal. So the numerator, sine squared theta times cosine over cosine squared theta, stays the same. And then I flip the sine squared over 1 to be 1 over sine squared. And I notice that the sine squareds cancel out. So now I have 1 over cosine squared. Is that something? That is secant squared. And there we're done. Was a little bit. Okay. Bye, Gabe. We'll see you later. All right. Let's take a look at this next example. Kate. Sure. What should we do first for this one? You cannot do that. 1 minus sine is not equal to cosine. No. 1 minus sine squared is equal to cosine squared, which is a big difference. But not a bad idea. But definitely not right. You cannot cross. So cross multiplication is a solving technique. Much simpler than any of these things you guys have said. Common denominator. What would the common denominator be? 1 minus sine times cosine. Good. Right. So the first one will multiply by cosine. The second one, 1 minus sine. Everybody okay with how I got to here? Let's take a look at what we have going on in our numerator here. Yeah, where is there a 1? Cosine squared plus sine squared is
1 minus. The marathon. It was like a marathon. No, it was David and his two sisters running through. That's hilarious.
okay. Now what? Now what? Okay. And then what? And that is secant. Let's just stop here. This is enough.